The smooth endoplasmic reticulum plays a main role in the production of many various lipids, including phospholipids and cholesterol, both of which are required for the production of most membrane lipid bilayers. Most membrane phospholipids are derived from glycerol and synthesized in the cytosolic side of the smooth ER membrane. The already enclosed membrane provides a suitable environment for phospholipid synthesis, as a hydrophobic environment is provided inside the lipid bilayer for the hydrophobic tails, and a hydrophilic environment on the cytosolic side for the hydrophilic polar head groups. Transported by coenzyme A carriers are two fatty acid chains, and these combine with glycerol-free phosphate via an enzyme that is bound to the cytosolic side of the ER membrane. Phosphatic acid is formed, and this phospholipid is inserted straight into the ER membrane. Phosphatic acid is converted to diacylglycerol via a phosphatase. Different polar head groups are then added to diacylglycerol via enzymes in the membrane of the ER, forming different phospholipids with various properties. As these newly formed phospholipids are only added to the cytosolic side of the membrane, enzymes called flipases pull them across, ensuring equal growth of both layers of the membrane. Transport vesicles bud from the ER membrane, carrying newly synthesized phospholipids to then fuse with the membrane of other organelles where they are needed, such as the Golgi or plasma membrane. A significant functional difference of the smooth ER is its role in detoxification. Every day we encounter numerous toxins, the majority being xenobiotics such as antioxidants, drugs, pollutants, food additives, or hydrocarbons. Endogenous toxins include any waste product of normal metabolism, such as ammonia, peroxides, aldehydes, or reactive oxygen species. The smooth ER provides a separate compartment within the cell for synthesis and storage of the detoxification enzymes. It is extensive in hepatocytes, more specifically in the sinusoidal system. This is a sophisticated multicellular hepatic structure established for filtration of blood and subsequent extraction of toxins. Toxins leave this system either chemically modified or broken down into harmless products. The smooth ER deals with xenobiotic and endogenous toxins in different ways. There is a huge variability in the type of xenobiotic the body will encounter every day, so the body uses a common mechanism to deal with all of them. Detoxification of xenobiotics has 3 stages: modification, conjugation, and excretion, the smooth ER being heavily involved in the first 2. Modification. A hydroxyl group is formed, making the toxin water-soluble. The enzyme cytochrome P450 takes an electron from NADPH and transfers it to molecular oxygen. The oxygen then combines with a free hydrogen ion and is added to the toxin. Conjugation. Transferase enzymes conjugate the now lipophilic toxin with a charged species, enabling it to be targeted for cell excretion. Many different endogenous detoxification systems exist for dealing with the regular influx of natural waste products. For example, an antioxidant system flushes out reactive oxygen species created by all mitochondria. Aldehydes are disposed of via the glycoxylase system, and so on. The smooth ER is able to proliferate in response to high amounts of toxins, and then return to its normal size once they have been eliminated. Indeed, this role of detoxification is so important that the smooth ER will prioritize it over a lipid metabolism, explaining why people exposed to a large amount of toxins, such as alcoholics, tend to have a lipid buildup in the liver. Calcium is needed for many of the body's functions. For example, in muscle contraction, the calcium needs to bind to troponin to allow the myosin and actin filaments to bind to each other. It is also needed to bind to calmodulin, which mediates the control of many enzymes and cellular functions. It is also needed to initiate neurotransmitter release in synapses, where the influx of calcium through voltage-gated calcium channels causes the neurotransmitter vesicles to be released. However, this calcium needs to be stored when it is not being used. This allows it to be released in high quantities when required. If it was free-floating calcium, it would not be able to use for these functions. The smooth endoplasmic reticulum is where it is stored. In non-muscle cells, the calcium enters by the calcium ATPase, which catalyzes the hydrolysis of ATP, moves calcium into the lumen of the smooth endoplasmic reticulum at the same time. Inside the smooth ER, it needs to be stored, and this is done with the use of calreticulin and calnexin, proteins that are involved in a chaperone role. The calcium is in an inactivated form when bound, but the proteins also need the calcium to do their chaperone role of helping misfolded proteins. The calcium leaves the lumen by ryanodine receptors aided by the concentration gradient from the high concentration of calcium ions stored in the lumen. This can happen from an IP3 signal that causes the release. In muscle cells, the endoplasmic reticulum is called the sarcoplasmic reticulum. This has the important job of muscle contraction, so calcium storage is very important for sustained contraction. The calcium enters by a specialized calcium ATPase called SERCA, and inside the lumen is stored with calsequestrin. It leaves by the same route of ryanodine receptors as the non-muscle cell. SERCA is regulated by phospholamban, which would normally inhibit SERCA by associating with it, but on beta-adrenergic stimulation the association is reduced and it is activated to start taking back up calcium ions into the sarcoplasmic reticulum and leads to muscle relaxation. This in turn contributes to the inotropic response of enhancing contraction of the muscle even more. Diseases associated with the calcium homeostasis of the smooth endoplasmic reticulum are dilated cardiomyopathy. This was shown by Norton in 2003. It's a heart muscle disorder that has been related to mutations in the phospholamban and its regulatory role. Furthermore, asthma has also found that the inflammation is from SERCA downregulation. Moreover, calreticulin is also associated with many autoimmune diseases. A role of the smooth ER is to break down glycogen. Glycogen is a large complex molecule in comparison to glucose, a smaller, simpler molecule that is generally permeable to most membranes. Glucose obtained from glycogen is able to leave the cell in times of need, such as in response to increased muscular activity. Glucose 6-phosphate has been obtained from glycogen via a series of enzyme-catalyzed steps in the cytosol of the cell. It enters the lumen of the smooth ER from the cytosol of the cell via a glucose 6-phosphate transporter. Glucose 6-phosphatase, an enzyme anchored to the inner cisternal membrane of the ER, then hydrolyzes the phosphate group of glucose 6-phosphate, thus removing it, creating glucose and inorganic phosphate. Glucose can now leave the lumen of the ER and move into the cytosol of the cell via transporter proteins. Glucose in the cytosol is then ready to be transported easily out of the cell via a GLUT2 transporter across the membrane into wherever it is needed.